Okay, so thank you for the introduction and thanks to the organizers for this opportunity. So we will work over the field C in a minute. I'll come to what's the question that we are trying to answer. Before that, I want to set up some notations. So X is always a smooth projective curve of genus at least 2. Line is a line bundle. L is a line bundle of degree 2g minus 1. And we will denote this to be the moduli space of rank 2 stable vector bundles on X with fixed determinant L. The main object of study in this talk is this subvariety inside the moduli space, where we look at all those bundles which have uh, at least 2 linearly independent global sections. They are called the Brill-Noether subvariety. So they are known to be of dimension at least 3g minus 5 when the degree is 2g minus 1. And this projective space of extensions of L by O will be denoted by PL throughout the talk. They are important. The aim of this talk is to study, to answer some question about when these varieties will be unirational or stably rational, and for low values of the genus. Okay, so since we are looking at rank 2 vector bundles, the well-known way of studying them is through extension maps from a projective space. So there is a, okay, so before going into all these things, let me just say what is the, what are we trying to do? So we have this E of X1 LO dual. So from here, there is a rational map to the moduli space. And we have this subvariety inside this. So all we are interested in studying rationality of this subvariety using this map. So what we do is we look at a certain hypersurface H inside this, and we restrict the rational map here, and this is also rational, and we show that this map is dominant. It's a rational map, and we show that this is dominant, and then use the known results about rationality of hypersurfaces in a projective space to conclude something about this using the fact that this is dominant. And in fact, we showed that this map is actually generically a projective bundle, a P1 bundle. So that helps us to extract some information about rationality here from those that are here. So yeah, so next two slides, they are maybe well known to the experts, but I just explain how do we get the rational map. So from X is a smooth curve, from X cross PL to X and PL we have these projections, and there is an universal exact sequence on X cross PL, which has the obvious property that if you take a point, if you start with an extension and you restrict this to that point, you get back this same extension. And how do you get that this universal extension is you just break this into this decomposition, which is Punnett formula, and look at the identity element here. That gives you an extension that is precisely this universal extension. So this EL here gives you a rational map because you have to restrict it. To land here, you have to restrict to those stable things. And it's well known that if degree L is 0, this map, the domain is empty, and degree L is 0, 1, or 2, this is actually a morphism. And now, in the next few slides, I'm going to explain exactly where this map is not defined. It comes out as a secant variety. So if D is an effective divisor, you have a natural map from L dual to L dual of D, and you define the linear span of an effective divisor denoted by D closure to be projectivization of the kernel of this homomorphism. And you can compute the dimension because this is a surjection. And this is very basic. So one can describe the semi-stability of the middle term or stability of the middle term, because here semi-stability is same as stability because rank is 2 and degree is odd. And what happens is that you can describe stability of the middle term exactly by in terms of these linear spans of these divisors. So if E is not stable, if and only if the extension is in some linear span of degree, at most half of the degree of the bundle, and not semi-stable if degree is strictly less than, and semi-stable but not stable, which is strictly semi-stable if degree is exactly degree of E by 2. Okay, so X will be embedded in PL because we are assuming degree to be 2G minus 1, which shows that this degree is at least 2G plus 1. And we define this secant variety by taking the union of all these spans. Sec R for any integer R is you take union of these spans for when degree is R. And so one can check that sec1 of X is actually the curve X, and these inclusions are there. And the closed subvariety sec G minus 1X of PL is precisely the locus of extensions, with middle term being not stable. So this is the bad locus, and this has to be thrown out to get a morphism. So so Bertram actually shows that he shows that he resolves through a sequence of blow-ups. He resolves this rational map. He resolved this rational map into a morphism, and from his proof, it follows that phi L will be birational. It's of course known the moduli space is rational. From the works of Schofield and King, but this is actually one proof. When degree L is 2G minus 1, phi L is birational, showing that moduli space is rational. Yeah, so as I said, I'm going to use this extension map to study some properties of, rationality properties of the Brill-Noether loci. Yeah, so as I said, this hypersurface H, so how does it come? You just you have this universal extension, you just push forward that universal extension to PL, and you get this long exact sequence. So because of the degree assumptions, H0 XL and H1 of XO both are of dimension G, so you get a lambda is a G cross G matrix, and then you define the closed subscheme of PL corresponding to the ideal shift generated by determinant lambda, this map. And one can check that this is precisely given by all those extensions where the middle term has dimension, the global section, it has at least two linearly independent global sections. So what we show is that, so in these cases when the degree is 2G minus 1, there is a stable rank 2 vector bundle which lies inside the hypersurface. And moreover, one can choose E to satisfy H0E to be 2. So the generic bundle inside the generic extension inside the hypersurface will have global section at least exactly 2. So the point that stable, there is a stable, there is an extension with middle term being stable is not a, it is easy to see that, so if H is entirely contained in the bad locus, then a simple dimension count gives a contradiction. So there has to be an extension with middle term being stable, and a little bit of more work will show that you can always choose E to have, an extension with middle term being stable and H0E to be 2. So, so these subvarieties are non-empty is already itself a complicated question. So these are the results which are known by the work of Biswas from 1991. So when you don't fix a, this is when you don't fix a fixed line bundle, not a fixed degree case and not the fixed determinant case. So it has at least one component of the expected dimension, which is 4g minus 5. It need not be irreducible. And a generic E inside this variety will satisfy H0E to be 2. But if the curve itself is generic, then this is the only component. This is a result of Biswas from 1991. And there is another one from 2010 that if X and L are both generic with the same degree, degree L is 2g minus 1, then this is non-empty and has at least one irreducible component of the expected dimension. So this is for the fixed determinant case. So from here, it's not difficult to show that this, in our case, actually W1X2L is irreducible. This is what we show. It's not difficult to show. And so now what we do is that we restrict. Now because of the earlier proposition that I proved, this V is a non-empty open subset of H. You throw out the bad locus, intersect it with the hypersurface. This is a non-empty open subset of H. And it now restricts this phi L, this extension map now restricts to a morphism from V to the Brill-Noether. So now basically the main thing that we showed is that this is actually a P1 bundle. This is birationally equivalent to a P1 bundle. So, before that we show that this is dominant, and and this is actually a P1 bundle is what we show. And using this fact, so why P1 bundle is important? Because we will show for genus 3 the variety is stably rational. So what does that mean? So we say a variety is stably rational. So V is, so any variety is stably rational if V cross V K is rational for some K. Oh, so the thing is that we use this thing. It's birational equivalent to a P1 bundle to show that this variety is stably rational, because in this case it is known that the hypersurface will be stably rational from some earlier works. And when G is 4, we show that this is unirational, this W1X2L. So for that I need to introduce these notion of incidence varieties and the projective Grassmannian. So so this P will parameterize all the degree D hypersurfaces in Pn. V here is V is just this space. And we look at GRN. So this Grassmann variety parameterizes R-dimensional projective linear subspaces of Pn, and we consider the incidence variety. It is, I mean, these are not important, but it is known that this is non-empty and has this dimension. And you look at these projections from IRND to P and GRN. So under these conditions, P1 will be surjective. Now, what are these conditions is not important. The fact that P1 is surjective will say that you take any projective, you take any degree D hypersurface, then there is a projective linear subspace, R-dimensional, which is contained entirely inside that hypersurface. So that's going to be important because it's a result of Marchisio from 2000 that a degree D projective hypersurface which contains a linear subspace of dimension D minus 2 is unirational for D equal to 4 and 5. So already these are, very known for very special cases, and it remains a conjecture for higher D, and the conjecture is due to Conte, Alan Conte, I forget the name. So, but for D equal to 4 and 5, we show that when using this result of Marchisio, when genus is 4, this quartic hypersurface is unirational. So H will always be of degree G from the definition. It's a degree G hypersurface. So when genus is 4, using this and these computations, one can show that this is unirational. And therefore, since this is a dominant rational map, you get this variety to be unirational. So unirational means you have a dominant map from a rational variety to your variety. And finally, to wrap up, when G is at least 5, we could show that this is chain connected by Hecke curves of length 2, and some small computations about the hypersurface, we call this Brill-Noether hypersurface of their Chow groups for low genus. So the hope was to compute Chow groups of this, but the fact that it's only a projective bundle, it's not an honest projective bundle, but generically a P1 bundle. So I'm not quite sure how to do Chow groups of these varieties. So yeah, so that's it. So these are some important references. So thank you.
Okay, questions? So, very often the results in Brill-Noether theory are for general curves.
Yes.
But
is
this for general curve?
Yes.
Oh.
Yes. Non-emptiness results for Brill-Noether, and it's irreducible. It's true only for when X is general.
But did you assume that we're on a general curve?
Yeah.
Okay, yes, I missed that. I thought it was for any curve.
Yeah. And H will be irreducible. One can show H to be, because that's important for rationality.
This isn't directly related to your talk, but is there some analog of Brill-Noether theory that you're familiar with where you don't look at global sections of the bundle itself, but global sections of the endomorphism bundle?
I have no idea, but sounds interesting. I have no idea.
Thanks.
More question?
So I have one question. So I know that second varieties are related to Hecke modifications. And I saw that you mentioned Hecke curves.
Yes.
Are those the P1s that appear? You mentioned a P1 bundle. No. No, it's different. Okay. So how do these Hecke curves appear?
Yeah, so I have to go a lot. I have to say a lot of things.
Sorry?
So it's, so I have to say, yeah. No, I mean, I have to introduce a lot of things.
Okay. No more questions? Okay, let's thank
Thank you.
Pritthijit again.